I just want to make sure that it actually will go live.
The wind is strong.
Does not seem so.
But yeah, you see that rain falling
Through the rain.
top of the building. Yeah.
And the
Okay,
clouds
so there's 30 people watching already.
The PowerPoint is open.
Yeah, I will open it.
You can?
I'll do it, yeah.
Okay, please.
So there's some delay. So, do you want to wear this?
Why should we? Is somebody talking to us when we present?
No, but I can hear because I have my.
Studio now here in the studio. So, yeah, maybe I'm going to sit here. So that's now look if you see now there on the skyline, look how the cloud interface. Yes. Moving. Yeah. See the clouds this direction. There is some potential. Look, you have some things flying everywhere. Yes. Clear the water on top of that. Yes. How it's swept. Yes. That's already serious speed. Lady there, Victoria, can be happy that finally something is happening.
So is one of you going to monitor it on your computer to see what it looks like?
I can take mine.
Sure. Just put the sound down though, so it doesn't feedback. But I put this one up right now.
Yes. You see the difference of 50 years.
Wow.
So I see the web yes. See your first page. Yes. Oh, beautiful. So broadcasting. Yes.
And if I change it to the back. So now you should.
Yes.
And now it'll change back and go to the.
Yes. Yeah, sure. Right. Fantastic. The gift of ubiquity.
Yep, you can hear me okay? Yeah, so it's best to have the headset on. We have quite a lot of viewers.
What? 57.
Probably more than if we were doing this. This is great. So it turned out using the hotel's Ethernet was not such a good idea because they had some security problems that caused it to connect badly. So when I'm using my Wi-Fi thing, it's working fine. We'll just wait. Yep, we have 1 more minute to go. Yes. 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 They already see it, yes. They hear us, yes. They can hear you speaking right now. Yeah. But you should turn it down because it feeds back. Okay, so listen to the wind. So should we get started, gentlemen? Okay, let me start this. Yeah. Okay, gentlemen, guys, we're on the air. Okay, hello. Good afternoon in Osaka, Japan. My name is Nigel Goldenfeld, and we are broadcasting an unofficial symposium, which was originally scheduled for today at the 50th anniversary of the Japan Society for Fluid Mechanics. And this auspicious occasion has been graced by nature with a Category 3 typhoon, which is just starting to sweep through the city. So we're broadcasting from the hotel, and we wanted to present our work to the original participants and to anybody else who is joining us through YouTube. So, so we have we're going to give 4 talks, each of which is about 30 minutes. And if you want to send questions, you can do so through YouTube, through the chat. So let me just type something in. There we go. So there's a chat window. So we don't have everybody here, unfortunately, but we have most of the speakers. So I think you'll find this a very interesting and varied symposium. Okay, so I'm going to act as chairman because it's simply my computer that's being used. So the first speaker is Professor Tsutomu Kambe, who's from the University of Tokyo. And his talk is going to be about the history of the Japanese Society of Fluid Mechanics. That's the first part of his talk. And then the second part of his talk is some new perspectives on mass conservation and waves and fluid. So please wait 1 second while I just transfer over to him, and then we will get underway. So let me pass over to you, Professor. Would you like to use the headset?
Yes. Useful. Good afternoon, everybody, a member of the Japan Society of Fluid Mechanics. Yeah, that's right. Start. Yeah. Congratulations of the 50th anniversary of the Japan Society of Fluid Mechanics. Unfortunately, today we missed the opening address of President of the Japan Society of Fluid Mechanics, Professor Michio Yamada. We think we are very grateful for the effort of all the members of the organized committee and the president, Professor Michio Yamada. So to thank their effort, we discussed to make this an official conference on the website. So let us start. So this is, you can see the difference of the landscape in Tokyo near the Tokyo Tower. So this is a difference of 50 years. And I will talk about some history, pioneering studies of the Japanese scientists. And in part 2, I will talk about the new perspectives on mass conservation law and waves in fluid mechanics. You see the difference of Shinkansen. The top one is first Shinkansen, and lower bottom one is new Nozomi Shinkansen. And this is the area near around the Tokyo metropolitan government area. And you see the right-hand side, Tokyo Shibuya, about 60, more than 60 years ago, and last year. And left-hand side, Osaka Shinsekai Tsutenkaku area. And you see the difference 100 years ago and last year. Now, we talk about the pioneering studies in Japan around 1960. Those studies led by two distinguished scientists, Professor Ichiro Tani and Professor Isao Imai. And first, I'd like to talk about the distinguished study of laminar viscous flow around a circular cylinder. Imai showed the flow field far from the cylinder and asymptotic solutions of the viscous flow around the cylinder. And that was published 1951. And based on this far-field solutions, analytical solution, his research assistant, later Professor Mizuo Kawaguchi, made the DNS, digital numerical simulation, by using hand calculator. And he told me it took a year and a half to finish his computation. So, but recent computer, probably it can be finished within 1 second or 1 minute. And those studies, analytical study and numerical studies, are compared by the experimental study by Professor Taneda. He published his work 1956, and this was the streamline was visualized by milk, condensed milk, and compared, and they found amazing similarity between the numerical solution and visualized solution. And this provided a strong evidence that Navier-Stokes equation can describe steady laminar flows at moderate Reynolds number up to about 40. And also, in addition, provided a stimulating hint for later development of the method of matched asymptotic expansions, later developed by Proudman, Pearson, and others, Kaplan, Lagerstrom. But those three workers didn't say their combined works contributed to the development of matched asymptotic expansion. But I personally feel strongly, actually their works contributed the development of new method. That is why I'm showed to the audience their work to commemorate their work and commemorate the Japan Society of Fluid Mechanics. And this comparing the actually enlarged diameter, so the diameter all same, and their visualized pattern and computed patterns are almost same. And next topics of the pioneers is the study of stability and turbulence. Professor Tatsumi, he studied turbulence. He started his study when he was in United Kingdom, awarded by the British Council scholarship. And he published his work 1957. And connected with the turbulence study, linear stability analysis also were carried out by the Tatsumi group. Professor Kakutani published this linear stability analysis of two-dimensional big red jet and predicted the critical Reynolds number is about 4. And also, next, the Tatsumi's group, Professor Kanefusa Goto, published a linear stability study of free shear flows. And in parallel with the analytical computational study, Professor Hiroshi Sato did experimental study of stability transition and turbulence by using wind tunnel. His work was published 1960. And next, third topic of the pioneer is streamwise vortices in boundary layers. Late Professor Ichiro Tani published an article in the first volume of Annual Review of Fluid Mechanics Boundary Layer Transition. At the time of 1960s, there was a gap between the observed phenomena of boundary layer transition to turbulence and the stability study of mainly linear analysis of 2D disturbances. Formation of 3D disturbance is required for the flow transition to turbulence in the boundary layer. There was a gap. Associated with the three-dimensionality, there was an evidence of streamwise vortices in the boundary layers. This transition problem was reviewed by the late Professor Ichiro Tani and studied by Tani Komoda, collaborating with Professor late Leslie Kovasnai, staying in Tokyo at that time. They collaborated. The vortices cause a redistribution of mean velocity field. Later, the strict structure in boundary layer flows was interpreted by this mechanism. And fourth topic is nonlinear waves. Hashimoto was a professor when I was a research assistant. And he studied vortex motion. I did experimental study of vortex motion. Fluid motion driven by locally concentrated vorticity can be described by local induction law. It is known at that time. Hashimoto transformed the law into the nonlinear Schrödinger equation and obtained the soliton solution of first vortex soliton solution about deformed vortex filament. And second, Professor Akira Sakurai studied blast wave. A blast wave is usually generated as a big shock caused by a powerful explosion, such as supernova or atomic bomb. Unlike the sound speed, the velocity within the blast wave is not constant, always larger than the sound speed. Certain exact solutions of the blast wave problem were given by Sakurai for each of spherical, cylindrical, planar symmetry, and he cited G.I. Taylor's work of 1950. So about 52 years ago, from this year, there was held a symposium, international symposium on boundary layers and turbulence, including geophysical application. And this group photograph remains, and we can recognize many distinguished scientists at that time. Gertler, Frankel, Tani, Roshko, Yagrom, Kvasnai, Hintze, Landau, Pai, Krebanov, Bachelor, Lighthill, Safman, Rojansky, Bechov, Benny, Laufer, and many Japanese scientists. Professor Tatsumi is seen here, and Professor Hashimoto is seen here, and Professor Kakutani of Osaka University is seen here. Then I'd like to talk topic about Bachelor and Taneda. So D is missing here. After the Kyoto Conference, 1966, George Bachelor visited Taneda's laboratory at the LIMS Institute, Kyushu University. And he was interested in various visualization experiments carried out there by Taneda and also by Okabe Inoue at the same institute. He cited a number of George Batchelor cited a number of photographs of their visualization in his textbook. We can see the cover of his well-known textbook, An Introduction to Fluid Dynamics. And the rightmost picture was taken from my book, the book I have. We can see the signature of George Batchelor, 1975. And Taneda was scouted by Professor Hikoji Yamada to his laboratory in Kyushu University. And Professor Hikoji Yamada is the father of the current president of Japan Society of Fluid Mechanics, Michio Yamada. And Bachelor's Prize is now a UTAM Award Prize. This was discussed at a UTAM Bureau meeting about more than 10 years ago. First, it was proposed as a JFM Prize. But at that time, I was a member and I commented, Bachelor Prize might be appropriate. And there was the relation Tani and von Karman. 1960, there was a UTAM symposium, MHD, at Williamsburg in USA. And there were several Japanese participants there. And also, there was fluid physics section at JPL, NASA. There, many Japanese scientists were invited. Here we can see the von Karman and Professor Tani at the seminar meeting in California. Now, I'd like to talk about the second topic, part 2, new perspectives on mass conservation law and waves. We begin, first of all, with the following recognition. Conservation of energy is related to time translation symmetry invariance. The fundamental conservation equations of fluid mechanics are derived as non-relativistic limit from the relativistic fluid mechanics. From a single relativistic energy equation, we have two conservation equations in the non-relativistic limit. One is energy conservation equation of traditional form, and another is continuity equation. Symmetry implies a conservation law. This is Nesard's theorem, proposed 100 years ago. Then we ask, what kind of physical symmetry implies the mass conservation law? From the textbook of Randall Griffith, there is a section, relativistic fluid dynamics. There we can derive the energy equation. So in the Randall Griffith textbook, this equation is not shown, but describing actually this form. And the first term, this gives the rest mass part. And the second term, the flow energy part. And the smaller order term, the final non-relativistic limit. And in the non-relativistic limit of small velocity compared with light velocity, we have two. From the first time, continuity equation, second term, energy conservation equation. The textbook Fluid Mechanics of Randall Griffith begins with the first section. First section is equation of continuity, deriving this equation and mentioning just This is one of fundamental equations of fluid dynamics, not others. So Nesa's theorem was proposed 100 years ago, 1980. Symmetries imply conservation laws. And symmetry in physics means invariance property with respect to transformation. So one example I shows Lagrangian densities of fluid dynamics, ideal fluid dynamics, and requiring invariance of the Lagrangian density with respect to local gauge transformation, coordinate transformation. Capital X means a Lagrangian coordinate for a fluid particle, fixed particle. And taking variation of the Lagrangian coordinate by delta x k, then we obtain Euler-Lagrange equation. Then Euler-Lagrange equation is shown here, well known, so I don't explain the detail. Then next, so to derive the Euler-Lagrange equation, it is assumed the variation of Lagrangian density vanishes. But next, simple variation without assuming vanishing boundary values, we have this equation. So left-hand side is the Euler-Lagrange equation multiplied by delta x, and right-hand side is divergence of energy momentum tensor multiplied by delta x. This is a Nesa's theorem. Just a symmetry means vanishing Lagrangian variation implies the conservation law of Euler energy momentum tensor. So this is Euler-Lagrange equation imply conservation of energy and conservation of momentum. Then we look at the detail of the fluid mechanics. The energy momentum tensor of ordinary fluid flow is described like this, and conservation of energy and momentum is obtained like in the standard textbook of fluid mechanics. But conservation law of mass is assumed a priori to be valid. This is classical fluid mechanics. Then relativistic energy momentum tensor can be represented like this. In the Landau-Lifshitz textbook, it is described by sentence, but expressing in the matrix form, the relativistic energy momentum tensor is like this. So red part is a new relativistic term. And from this energy conservation equation is like this as shown before. From this, so from a single energy conservation equation, we have two conservation equations. And in the textbook of Landau-Lifshitz fluid mechanics, this first mass conservation equation was neglected or assumed to be valid a priori. Then he derives the non-relativistic energy equation. they derive the relativistic equation. And the momentum equation is like this. Red part is the new part. Oh, so so relativistic momentum equation is like this. So I skip the detail. So gauge invariance implies the mass conservation law. This is a new proposal. So to derive the mass conservation law from some symmetry, gauge symmetry, we propose the Lagrangian, same as electromagnetic Lagrangian, just notations changed, the same as electromagnetic Lagrangian, and take variation, and we can derive uh, this one, this equation. The left-hand side variation of Lagrangian, right-hand side variation of Lagrangian density, and if the and the variation in this case is a gauge field variation of gauge field, then this equation transformed to this form. So variation of Lagrangian implies vanishing of some conservation equation. This is just mass conservation law. So gauge invariance of Lagrangian density of the electromagnetic like Lagrangian density implies mass conservation law. So this mass conservation is formulated as a Nesard's theorem. Same by the same principle. So I propose in this way the mass conservation law implies a new field, new gauge field. So we propose the two fields. One is ordinary fluid flow field. The other is gauge field to assure mass conservation law. So the total field is composed of fluid flow field and wavy field. Flow field F and wavy field W. And the momentum equation is can be derived, and there is an interaction term between the two fields, two components, and that is just a Lorentz force in the notation, in the description of fluid flow. Energy equation, also there is a interaction term. Then I skip the details, so I will summarize the new proposal. So mass conservation law is represented by new gauge invariant fields. EB is electric like field, and B is magnetic like field. And the mass conservation law is interpreted by the Nesard's theorem. Conversely, the mass conservation law implies existence of new gauge invariant fields. This is the main proposal of this study. And the fluid flow field is acted on by the gauge field with a Lorentz-like force. And in this Lorentz-like force, gravitational force is implied by the scalar potential phi A. Fourth, the energy equation can be generalized to include the dissipation effect by a dissipative mass current. This can be an extension of the present formulation. This enables much higher rate of dissipation than the viscous effect. The concluding remarks. In Japan, more than 50 years ago, the study field of fluid mechanics did not have a fixed position in the academic community. In physics community, it was regarded as classical and applied mathematics, sometimes as macroscopic or phenomenology. While in the engineering community, it was regarded as being too theoretical or too mathematical. This situation was one of the motivations to establish our society, Japan Society of Fluid Mechanics. There was another motivation, which is not said explicitly, political motivations. I will explain it if I am asked. Fluid flow field. No. However, now I believe personally that the fluid mechanics should not be called as classical, but it is one of the simplest models of field theory of physical systems because fluid mechanics can be described by Lagrangian functionals and also by the gauge theory of theoretical physics. Fluid mechanics is not only based on the field theory of physics on the fundamental level, but the fields covered by fluid mechanics are diverse: geospheres, cosmic space, engineering, technology, biospheres, nanosphere, in particular atmosphere, ocean, climate, and many others. New age gives us new challenging problem. Now, this is the last slide. Amazingly, Typhoon is interested in our conference 50th anniversary. Typhoon is running over our heads now, so interested in our anniversary conference. Thank you for your kind attention.
So thank you for your talk. For those of you who are watching on YouTube, if you want to ask questions, please do so. There's a chat, I think, on the web. If you look at it on YouTube, there is a chat place. Yes. Can you just say to type something? I think it's possible to you need a channel. I think only if you're a YouTube user you can ask. Yeah, you need to have a YouTube account to ask a question. Yeah, so if anybody wants to ask a question, you can type into the chat box at the right, and I will pass the question along. So, meanwhile, maybe. So I think we will not take questions, unfortunately. But if some later if people figure out how to create a YouTube channel and they can ask questions. So why don't we go on to the next talk, which is what? Let me just look at my cheat sheet here. It's you, right? All right, so the next talk is from Fulvio Scarano from Delft, who is going to talk about some super cool advances in looking at large-scale flows with robotic PIV, and I'm particularly interested to hear this talk because Ron Adrian, who was perhaps one of the most famous inventors of PIV, was from the University of Illinois at Urbana-Champaign, which is where I currently work. So Fulvio, why don't you come in and let me help you get set up?
Like this? Yeah? Okay. Thank you, Nigel, for the very kind introduction.
I didn't really do much of an introduction. Let me give you your talk. So this is your talk.
Yes. Okay, can click here. Wow. Okay, are we ready?
We're ready.
Okay, I will start then the presentation. Before starting this presentation, of course, I owe a lot of. I'm very grateful to the organizers of this symposium, and I would like to thank all the organizing committee of the Japan Society of Fluid Mechanics for inviting me to give this talk in such a prestigious moment. And okay, let me start right away. Then the title of the talk, as you will see, is as a different nature from the previous one. We are speaking of experimental fluid mechanics, and I've decided to speak about some recent developments in the area of quantitative flow visualization. In particular, this is a particle image velocimetry. And it's very exciting to speak about some recent advancements and what can we do nowadays with the PIV at a scale that is larger than in the past, and by introducing the use of robots. So this work would not have been possible without a number of collaborators that I'd like to mention: Andrea Shakitano, Konstantin Jux, Jan Schneiders, David Engler-Faleros, and Fritz Donker-Davis from the TU Delft. We also have performed a number of experiments in collaboration with partners, the Dutch Aerospace Research Center, NLR, LaVision, the Dutch-German consortium of wind tunnels, and also Airbus. Part of this research has been sponsored thanks to a grant from the European Research Council. So we need to understand better aerodynamics at a large scale for a number of reasons. The societal relevance of the work sits mostly in the sector of aviation. Of course, I come from the aerospace engineering faculty, so aviation is in the core targets of my department. But also, in order to continue developing renewable energy strategies for with wind farms. And apart from that, there are other exciting scenarios, novel concept for transportation of people off the ground, personal air mobility. You see in the bottom left picture a prototype from the Lilium Group in South Germany. And on the right bottom, this is the solar car, the Nuna car, developed by the students of the TU Delft. And also in this case, aerodynamic design is very important in order to use the little energy that comes from the sun and propel this vehicle. In this slide, I try to summarize in a schematic way what have been the developments of laser velocimetry from the times of laser Doppler velocimetry. In the bottom right corner, you can see these blocks. They represent In the depth direction, they represent the velocity components that are measured, and in the height direction, they would represent the coordinates in the domain that is measured. For laser Doppler velocimetry, this is a pointwise technique. Therefore, they essentially sit on the ground and is a time resolved technique. With the advent of PIV, we have seen the initial setup of this technique was allowing us to measure the U and V component in an X and Y, so essentially the planar velocity component, and followed by stereoscopic PIV, and finally the third dimension, the three-dimensionality, came with techniques like scanning, light sheet technique, holography, tomographic PIV. A further step came with the ability of putting together high-speed hardware, typically kilohertz camera and diode pumped lasers, and measuring a velocity component in three-velocity component in a three-dimensional domain, time resolved. By doing that, as I will explain later, it is possible, invoking the Navier-Stokes equation, also to determine dynamical information, not only kinematic. I'm speaking then of pressure obtained from PIV experiment. So far, the experiment allowed only the measurement in a relatively small domain. In airflows, I often mention an iPhone or say a mobile phone or half a mobile phone, given the available laser power, and in water flows a little bit more than that. However, in order to face the challenges I was speaking before, we need a scalability of a technique to upscale the experiment, and the scalability is one of the topics that I will discuss in the presentation. Is obtained with the introduction of new tracers. If we allow the technique to have this property of scalability, then we speak about large-scale PIV. So all of a sudden we move from a smartphone, the size of a smartphone, to almost the size of a human body, so to the meter size. Finally, there is a last step to be made if we want to face the engineering challenges that are offered for complex systems, and that's ubiquity. Ubiquity is the everywhere at a single moment. I don't speak about ubiquity of position, but I will speak specifically ubiquity of direction of observation. Let me go to the next slide. In such an occasion, it's nice to draw a parallel with some activities in Japan that I consider seminal also to what I present in this presentation today. So on the left we see this beautiful painting from the middle of 19th century from the Hiroshige school, and here we see waves and vortices, and it's something that we expect also with this huge typhoon hitting Osaka today. In 1967, already Ryosoku Kinoshita was studying from aerial views of channels, was trying to apply correlation methods and track the motion of waters in case of so motion of movement of flowed waters with aerial photography. To be then more specific and to see where how early PIV has also started in Japan, I like to mention this work of 1987 from Kimura, Takamori, and Inoue, where they have studied the flow, the complex flow past a cylinder at already moderate Reynolds number, and from highly seeded images they could obtain instantaneous velocity field. Where I find an important thing is that in Fukui, so not too far from here, took place the first workshop. At that time, it was called the workshop on particle image velocimetry in 1997, and it was chaired by Yamamoto and Kobayashi. And this workshop then ended up in a very successful line of now biannual conferences on particle image velocimetry. So it's so looks like many things have started in Japan that now have a worldwide impact. So the outline of the presentation today is as follows. I will speak first about three-dimensionality. How do we reach three-dimension in the measurement domain with the principle of tomographic PIV? Then I will mention an important step that is from kinematics to dynamic information, so from the velocity to the pressure through the use of momentum equation. And I will just give a glance of a few fundamental studies that have been done presented in thanks to tomographic PIV. Then I introduced the concept of scalability and what are the techniques and methods to perform large-scale experiments. Most hangs on the availability to have these large tracers, helium-filled so bubbles, in aerodynamic flows. And I will show that with two experiments, one on a vertical axis wind turbine and other experiments on ground vehicles. To come to more recent developments that give us ubiquity and versatility, I will introduce first the concept of a new configuration called the coaxial volumetric velocimeter, introduced by Schneiders et al. The work is published just this year. And this work is connected to the other one of robotic PIV from Konstantin Yuks. And I have some cool, nice applications, both for sport aerodynamics and for aviation. I'll conclude with some perspectives. So the concept of tomographic PIV is well described in a number of publications and also on both the two PIV textbooks, one from Adrian and Westerville and the other from Marcus Raffel and co-workers. In its essence, tomographic PIV requires the same equipment as for planar or stereo PIV, only the cameras need to be more than two, typically 3 or 4, or in some groups more cameras are used, and the laser is the same laser used for PIV. Instead of illuminating in a thin domain like a light sheet, we expand the sheet into a slab, so a thick domain. Once we obtain images of the tracers, these tracers can be at any depth in the volume, and they are imaged from the several independent views of the cameras. They are the novel component of tomographic PIV is the tomographic reconstruction, where the multiplicative algebraic reconstruction technique is used, inspired to medical tomography. And once we have the three-dimensional distribution of light intensity in at time t and t plus delta p, we apply the cross-correlation techniques and we obtain vectors in 3 dimensions. So a number of studies have been performed in the recent past, say in the last 5 to 10 years, and they deal a lot with transition. As you can see in the top left corner, for instance, Elsinga studied the transition of a boundary layer from laminar, the abrupt transition in this case, with the zigzag tape. The boundary layer undergoes transition, and Elsinga could identify the initial stages of transition with the coherent structures formed until they become more chaotic in a fully developed boundary layer. If instead a transition is forced with a single element, this is a micro ramp, this little triangle that you can see in the right top figure. This is the work of Chinchinier. And in this case, instead, the boundary layer is forced and forms hairpin-like oscillations that later on develop and self-generate, say, propagate into what ultimately becomes a turbulent spot. More recent work has focused on the instability of the boundary layer on swept wings. This is the work of Serpieri and Kotsonis. And in the figure in the bottom, we can see these unstable waves. These are the primary modes. On top of these primary modes, there are also secondary modes of more of a Kelvin-Helmholtz type. And in animation on the bottom right, you can see the pattern of transition in a round jet at Reynolds 5000. The yellow donuts are clearly vortices that are formed in the free shear layer, and progressing downstream, they undergo pairing and followed by a sudden abrupt growth of the azimuthal waves that brings them to breakdown. I think it should be clear to all the audience that if the flow becomes less symmetrical, the need for a three-dimensional technique becomes all of a sudden more clear. This is the case for these swirling jets at a different value of the swirl number. So the swirl number increases from 0.2 to 0.6 going from the left. And in gray, you see the axial velocity component, whereas in this multicolor palette, you see the vortices that are formed in this around the shear layer. So the complexity of the flow is such that if you would like to represent it with a plane, it's really difficult to understand what are the mutual interaction and what is the overall organization of such flow. So I think that by this application, one has demonstrated the usefulness of tomographic PIV to inspect fundamental problems in fluid mechanics. An important kind of side dish that comes from the ability to measure in 3 dimensions is the pressure from PIV. Everything hangs on the use of the momentum equation. You see it here on the left. We see that the gradient of pressure depends on the density of the fluid. If we assume an incompressible flow, the density is a fixed parameter, then on the material derivative of the velocity, and then on some viscous terms. If we perform divergence of this equation, we end up with a Poisson formulation of this problem. And this means that if we have a system that can measure the velocity in time, and we represent the material derivative of velocity by decomposing it as a local Eulerian fluctuation and v grad v, in fact, we can obtain the Laplacian of pressure. The solution of this problem, the numerical techniques are available, and this is what can be done. What's the use of this is that the idea is that in the future, perhaps we might not need to install so many little transducers patiently in all once a model is produced, the installation of these transducers is expensive, time-consuming, and sometimes is not even possible if the surface is too thin. Think, for instance, at the trailing edge of an airfoil. So I show here by a simple experiment what are the type of results that have been obtained. I think I have to accelerate, Mr. Chairman. Yeah. In this experiment, Jan Schneiders has measured the wake of a truncated cylinder adjacent on a wall, so in interaction with the turbulent boundary layer, and with recording at 2 kilohertz, performing a large-scale tomographic PIV experiment. I jump directly to the results. From the velocity data, we have obtained the pressure information, and we try to go as close as we could to the bottom wall, where also transducers were installed, and a fine pitch was obtained by moving the cylinder in several positions. So what you can see already from visual comparison of figure to the left top and the right top, the pattern is pretty much the same. And we also see that the mean pressure, oops, one slide went alone. The mean pressure is fairly well reproduced, which gives us a comfortable, say, position in stating that at least the mean pressure should be now quite accurately retrieved also with the PIV information. For the fluctuating pressure, this is a work in progress. The uncertainties are larger. Now, I have anticipated a little bit already about a large-scale experiment. How do we obtain the experimental scalability? If I take these 3 examples, you can see the tomographic PIV experiments are nice, but in fact they are limited to a few cubic centimeter domain. And when you go in a wind tunnel where aircrafts or aircraft models are tested, this domain is by far much smaller than the model being tested. Therefore, there is a large discrepancy between what we can do with the 3-dimensional measurements and what needs to be done for aerodynamic testing. In the diagram below, Giuseppe Caridi has mapped a number of experiments present in the literature, and he saw how the measurement volume compares with the acquisition frequency, and clearly they They are one the inverse of the other. And for high-speed PIV in particular, we see that we speak of measurement volume that is just very few cubic centimeters, on the order of 10 cubic centimeters. Let's see how can we introduce a larger volume for tomographic PIV. In the video that is being displayed, you see the typical setup of illumination with a laser and lenses, and then the high-speed camera watching the domain from the sides. And once the flow is seeded with standard microscopic droplets, 1 micron droplets, what you see by naked eye is just smoke. And now in the video here, this would be the image captured by one of the camera, if it's seeded by fog droplets. If you would use helium-filled soap bubbles, in the bottom here you see the bubbles generated by an orifice. These helium-filled soap bubbles have typically 100 to 500 larger diameter. Therefore, they scatter light in the order of 10 to the 4, 10 to the 5 more than the 1 micron droplets. The response time is about 1 order of magnitude longer than one of the droplets. And this is thanks to the property of being neutrally buoyant or nearly neutrally buoyant. In the bottom right, you see the type of devices that are being developed to obtain bubbles of different diameters, although this can also be done playing with the mass flow rates of helium, soap, and air. Producing bubbles from a single orifice is something. Producing enough bubbles in order to see the full stream tube and then perform a cross correlation with PIV around the model, it's something else. Here on the left figure, you can see the largest seeding generator we could produce in Delft. It is composed of 10 airfoils. A detail of the airfoil is showed here in the bottom. 10 airfoils with installed on each of these 10 airfoils, there are 20 generators at the trailing edge. Think that every generator produces about 30,000 bubbles per second. So we are speaking of a few million bubbles per second. And this is sufficient for flows up to a few meters per second. The first application I want to show you is that we wanted to try is the vertical axis wind turbine. Is shown, oops, it goes on its own. This wind turbine has the height of 1 meter, and also the diameter is 1 meter. So the scale is already quite large. The region where we measure is instead of about 10 by 20 by 20 centimeters. You can, in your mind, you can imagine a shoebox. And I will give first a movie. Here the bubbles are released by the seeding generator in a say intermittent way by accumulation in a piston cylinder. This was one of our first solutions. And as you see, with this movie was recorded with an iPhone, and still with an iPhone, with the sensitivity of this device, one could capture the light of the bubbles. Once this the light recorded instead by the scientific grade cameras was analyzed with the tomographic PIV and analyzed, giving us the vortices that are shed at the tip of the turbine blade. A second interesting feature of the helium-filled soap bubbles is that in some cases they tend to accumulate in the core of vortices. Therefore, they offer an alternative to visualization techniques already available for vortex visualization. This is an experience, this is actually my hand in the laboratory. With my hand, if I come in the way to the vortex, I cause an earlier vortex breakdown, and you cannot see the students, but this video was taken with all the classroom of students around. So students like a lot this new type of seeding because they can see also by naked eye, and they get very easily inspired by flow visualization experiments. Now, how do we move these type of techniques towards industry? You can see here a photo of an experiment done to measure the flow past a side mirror of a car. This was done at the Pininfarina laboratories. And Antonello Cogotti, that was a chief engineer at that time, he was very skeptical about the use of PIV in industrial application, because he typically saw that it takes 1 day or more to solve all the technical problems and before you have some results, and then it takes weeks to process the data. Therefore, here you can read. He was always ending saying, if you have once you reach a technique that can be useful, please make me a call, send me an email or a fax. And I think I will present now two technical solutions that bring us a bit closer to that level of versatility. The first one, that is a necessary step, is the coaxial volumetric velocimetry technique. Now what you see here, the typical a paradigm that has never been really changed in PIV is that illumination and illumination direction and imaging direction are typically orthogonal or quasi-orthogonal. Now, if you reduce the aperture between the cameras, and if we move even the laser in the same direction as the camera, we end up with the potentially a more compact configuration. The circle you see here represents a tennis ball. So the inspiration was, the idea was, can we put cameras and laser inside a tennis ball? When we would reach that, we are able to then move this device with our hand or with a robotic hand, which is what we did further. So the main idea is that this 3D velocimeter can be used as a torchlight to inspect, for instance, the engine of our car when the car doesn't start in the morning. What are the features of the coaxial volumetric velocimeter? It has a very small aperture, so this has some problems in terms of depth sensitivity. The probe is immersed in the flow, so it has some aerodynamic invasiveness, and has also a certain reach towards the flow because of the laser intensity decay. Therefore, helium filled soap bubbles are really needed as flow tracers. This technique, the coaxial volumetric velocimeter, would not work with regular fog illumination, fog seeding. It is needed to use high-speed recording. STB stands for Shaked Box. It's a technique developed by the DLR group, and is by now the most accurate approach to determine the velocity from tracks of particles imaged multiple times. I will explain shortly what is one of the shortcomings of the coaxial velocimeter, is that if you consider beta as the aperture, so the angle between the cameras, the largest possible angle, when beta is in the order of 60 or 40 degrees, the particles are still reconstructed in almost isotropic way, almost spherical. When for the CVV beta is in the order of a few degrees, then there is a large difference between the resolution in the X and Y direction and the one in the Z direction. How do we compensate for that? Then consider a particle moving along a trajectory gamma. The exact position would, the discrete positions would be taken at some intervals depending on the velocity of the particle. However, the reconstructed particle, or the particle including the measurement position uncertainty, would be much larger in the Z direction. As you see here, the epsilon Z is much larger than epsilon X. To compensate for that, we need a trajectory that is sufficiently long. And we have explained in an article with Kyle Lynch that the scaling of the uncertainty goes with the power 3/2 of the number of exposures n. So one can compensate in time to the coarse resolution in Z by using this approach. Let's see how this actually works when compared to a conventional tomography. On the left, you see a tomographic system that is observing the flow past a frigate ship, already with seeding of large scale, so with helium filled soap bubbles. And on the right, you see a first prototype of the coaxial velocimeter realized in collaboration with LaVision. The typical size of this box is 10 centimeters, so it's relatively compact. The laser certainly cannot fit in the box. The laser is much larger than that. Therefore, we need an optical fiber to transport the laser light. An application that was really ideal to prove the ability of the of this coaxial velocimeter is the need to study the aerodynamics of elite cyclists. A champion, Tom Dumoulin, with the Giant team, he was preparing, of course, for the following competitions, and Giant, in collaboration with Giant, we have been studying both the positions as well as the effect of a different type of clothes for the athlete. Because the athlete was not available to test in the wind tunnel, a 3D replica of the athlete was obtained, scanning his body and producing and 3D printing an identical body, which went in our wind tunnel. You see here the result in the right bottom corner, and this is more of an impression figure of the rider installed in wind tunnel with the back illumination. So the setup of robotic PIV was presented here. The seating system is an earlier seating system, is not the larger one that is available now, but was still sufficient for what we needed to do. And now the coaxial velocimeter is installed on top of a robotic arm. It's a collaborative robot, UR5. Here I don't have to say much because everything is self-explained in the videos. In the top you see Constantine that is setting up with a pad the initial position of the robot, and then programming all the paths of the camera in order to cover all the domain around the cyclist to the left and to the right. Then in the bottom left you see how the domain is covered piecewise, and the final impression is, for instance, this animation of streamlines around the cyclist. Clearly one can identify the topology of the flow with a stagnation point at the helmet front. That's very clear. Also with the number of recirculation between the chest and the legs, and of course very important, the recirculation around at the back of the cyclist and past the legs. In total, to build this data set were 400 views needed. This would have been impossible with tomographic PIV because you cannot mount and dismount the system 400 times. And with a total of 20 million vectors, one could map the velocity field and study the relevant aerodynamic features of this problem. I'm concluding. The second part is a more industrial application. This was done together with the D&W laboratories that had were hosting a model of Airbus propeller aircraft, and they offered an opportunity to demonstrate the capability of robotic PIV in that case. So now we are watching together the video that has been produced by D&W. And this is a time lapse where you can see the installation of the system, the robot being checked. There is a software that can control the robot, both for safety. The robot should not hit walls and certainly should not interact with the very sharp propellers. At some moment when the wind is on, also the seating system will be activated, and bubbles are produced that are making a seeded stream. The robot will then map the seeded stream at different positions, different cones, we call them cones, and then the cones are merged by knowledge of the position of the robot during the acquisition. All this gives an overall result. In this case, we could not measure the flow around the full aircraft because the wind tunnel is very expensive, so we could only make a half of the model and the wing. In particular, the attention was to the vortices formed by the nacelle and the interaction of the actuator disc or the propeller and the wing. Oops. Yes, these are some zooms to see. Well, once you have this three-dimensional data that is so detailed, again, a challenge is how do you look at that? How do you inspect the data? But this is a topic for another talk. Before concluding, I would like then also to yes, I would like to say that what I've taught today is the expansion of the experimental range towards large scales. This is done with the scalability of experiment and with robotics. So we can go from subcomponent level, typically say a wing or an airfoil, down to full system level. This is clearly very useful for engineering application. On the other side, if we want to study the small scale phenomena, for instance, energy dissipation, the origin of drag, then a current trend, and I see much research that is already directed in direction with the joining PIV and CFD technique in a data simulation framework. So I see that in the future, this data simulation framework, together with robotics and scalable tracer, will give an incredible expansion of the experimental range of PIV. With this, I would like to thank all the people attending the talk for the attention, and certainly I wish the happy anniversary to the Japanese Society of Fluid Mechanics.
Thank you very much for the amazing talk. All right, so again, if anybody has any questions, if we can't figure out the YouTube chat system, please feel free to send me an email at Nigel, Nigel, at illinois.edu, and I will be happy to forward them to the other participants, and we can ask them online while we're still on the air. So now I think we're going to go to the next talk, which is something completely different. It's by François Golse, who is from École Polytechnique, and this is on the kinetic theory of gases to models of aerosol flows. So give us a minute to just get set up here, and then we'll start the third talk, and then after François, I will in fact be giving the final talk. So okay, so here we go, François. So yeah, this ear comes off. Say a few comments before I start?
Yes, it would be good if you could scale back a little bit the picture, because it's too big. I mean the slides is not, it doesn't fit the screen.
I'll make it fit.
Okay, perfect. It will. All right. Okay, perfect.
Do you want to say something before I start the slides, or do you want to go straight to the slides?
Okay. You. You mean say a few words so I will go more. But I can say it while introducing. Okay, so dear colleagues, it's a great honor for me and a great pleasure to be invited to this 50th anniversary of the Japan Society of Fluid Mechanics. Of course, I feel sorry that the typhoon sort of modified this event to such an extent. But anyway, so I'm very grateful to the organizers of this conference for their kind invitation to Osaka. And the topic which I want to present in this talk
is going to be a description of recent works in collaboration with 3 colleagues of mine, Etienne Bernard, Laurent Desvillettes from the University of Paris 7, Paris Diderot, and Valeria Ricci from the University of Palermo. And so the maybe I could say a few words about the title. The title speaks about aerosol or spray flows, and let me start right away by reminding you of the definition of aerosol and spray. What I'm going to discuss in this talk is a very simple type of aerosol sprays consisting of a dispersed phase, which you might think of as solid particles or droplets immersed in a gas, which sometimes in the case of aerosols is referred to as a propellant. So therefore a class of models for aerosol sprays consists of a coupled system involving a kinetic equation for the dispersed phase, where you really have a statistical description of this system, or if you want, gas of particles or droplets. And on the other hand, you have a fluid equation for the gas or the propellant. And these system of the kinetic equation and the dispersed phase fluid equation are coupled by chiefly the friction force exerted by the fluid on each particle or droplet in the dispersed phase. So these aerosol or spray flows are important because they arise in very different context, physical context. I mean, you find them, of course, in diesel engines. You find them also in medical aerosols. If you want to simulate the diffusion of drug in the trachea and in the upper part of the lungs, then typically this description is going to involve some aerosol or spray flow models. And the issue which I want to address in this talk is how to justify some models used in this context. And before going to the mathematical description, mathematical physical description of these models, let me just say a few words about the various regimes that you might encounter in the context of spray flows. So here on this slide, I've taken from I think a lecture by Wright, which is called the Computer Modeling of Sprays, which you find on the internet. This diagram or schematic representation of the various spray regimes in the case of in the context of the diesel engine. So here you're seeing on the slide the liquid injection of you have this liquid which flows out of this nozzle. So at the beginning you have a fluid which is pretty much you only have the fluid, and then it gets injected in the gas, right? And so you have a finer and finer size of the droplets. Here these are typically droplets, and so you see from the closest portion of the flow near the nozzle, you have a regime which is referred to as churning. Then the size of the droplets is still significant, and you're in the so-called thick spray regime. And then you go from the thick spray regime to a thin and very thin regime. So the terminology I'm using here is taken from P.J. O'Rourke's PhD thesis already some time ago, 1981, and the situation which I want to consider in this talk is the one which is in the red box here, which is the thin spray regime. So typically it would correspond to a volume fraction of the dispersed phase small compared to 10%, less than 10% typically. So these are, the dispersed phase is relatively rare. Nevertheless, it's not so rare that it's a distinction with a very thin regime, in the sense that the feedback force, that is the friction exerted by the dispersed phase on the propellant, is not going to be neglected in the models describing the thin regime. Okay, so typically the model, the mathematical model I have in mind for this thin regime, and the one I want to justify based on the works I was quoting at the beginning, is the Vlasov-Navier-Stokes system. So this name indicates involves a Vlasov type equation. That is, Vlasov typically refers to a situation analogous to the Boltzmann equation of the kinetic theory of gases, except that there is no collision integral, right? So here the unknown for the Vlasov equation is going to be a capital F, which is a function of Tx and V, which is the velocity distribution function of the dispersed phase. Typically, it's the density of particles in the dispersed phase, which have velocity V at a position x and at time t. And of course, it's a non-negative function. So that's the unknown for the Vlasov equation. On the other hand, the unknown for the fluid equation is going to be the velocity field u of t and x, which is vector, and the pressure field P of T and X, which is a scalar field. And so here is the Vlasov-Navier-Stokes system here. The first equation starts with the advection equation for F, d by dt of F plus V dot grad x F. And then you have an acceleration term where here you see the effect of the drag force exerted by the fluid on the particle at the velocity v. Right, so there is here a kappa, which is a drag coefficient, which is a positive number, and here you have this term, which is under the divergence in v, which involves the relative velocity of the particles or the droplets with respect to the fluid. Therefore, it's the difference v minus u, u is the fluid velocity, times the velocity distribution function of the dispersed phase. So that's the Vlasov equation. And the second equation in the system, you recognize at the beginning the Navier-Stokes equation for a fluid of constant density. On the right-hand side, you have the term kappa times the integral v minus u f dv, which is typically the friction force exerted by the gas on exerted by the dispersed phase, on the propellant. Right, and then the last equation here, dv equals 0, is what remains of the continuity equation. We're in a regime which looks like incompressible fluid dynamics, except that here, of course, the gas is not obviously incompressible, but we're in a situation where the Mach number is low, and therefore it's been known for a long time that fluid dynamics in the low Mach number regime can be approximated by incompressible flows. All right, so here the parameters involved in this model here are kappa, the drag coefficient, nu, which is the kinematic gas viscosity, and there's another parameter which here is set to be equal to 1, which is the gas density, and which should appear in the momentum equation, in the Navier-Stokes equation. Good, so now right away, let me say that this system, this Vlasov Navier-Stokes system, is going to be established on the basis of some asymptotic analysis. So it's obviously a good idea to introduce the parameters which are useful in this problem. So here I have gathered the parameters in a table. So here you have typically first a length scale, which is the size of the container. Then you have NP and NNG. So P and G subscripts, they refer to the particles or the molecules in the gas. So typically NP and NG are going to be respectively the number of dust particles per unit volume, number of gas molecules per unit volume. Then I also will need the thermal speed of the dust particles and the gas molecules, Vp and Vg. And because I'm starting from kinetic modeling, we also need the cross sections for the various collisions involved. So the collisions between the particles and the gas molecules, SPG, which is this particle gas cross section. And there is the usual molecular cross section for collisions in the gas between the molecules. There are two dimensionless parameters which will typically govern the asymptotic regime I'm interested in, which is the first one is eta, which is the mass ratio of the gas molecules to the particle. And so there's another one, epsilon, which is going to be the thermal speed ratio of the particles to the gas. And we say right away that both these parameters are going to be small. Typically, the first one, it's kind of obvious. The gas molecule is typically much smaller than the typical droplet or the typical particle in the dispersed phase. On the other hand, the thermal speed ratio is going to be also small because typically we're in a situation where the thermal speed or thermal motion, if you want the variance of the molecular velocity around the velocity field, the bulk velocity u, is going to be much higher than that of the particles, which are much more massive objects and which therefore have less dispersion in their velocity distribution. Good. So with these table of parameters, then I introduce dimensionless quantities, and I'm going to scale the space with respect to the size of the physical domain. I'm going to introduce a time scale which is adapted to detect the motion of the particles. In other words, I'm introducing a time scale which is going to be the length, scale L, divided by the thermal speed of the particles, which is the slowest species, right? And with that, I'm going to scale the velocity of the particles and the molecules, denoted respectively by V and W, with respect to the thermal speed of each species, right? So typically you already see that there is a time scale which is adapted to the motion of the particles, but for which molecules are going to be rapidly moving objects. And with that, I introduced dimensionless velocity distribution functions for the dispersed phase. F hat of T hat, X hat, V hat is going to be F of TXV divided by NP over VPQ. So that's for the dispersed phase, and the analogous expression for the propellant, for the gas, in other words. And then with that, we write a Boltzmann equation, actually a system of Boltzmann equations for the, you think of the aerosols as a binary gas mixture, where one component in this gas is going to be the dispersed phase, and the other one is the molecules of the propellant. And so in the first equation here, so you see on the left-hand side the streaming, the advection operator acting on the dimensionless velocity distribution function for the dispersed phase, and on the right-hand side, I have an operator which is analogous to a collision integral in the kinetic theory of gases. But here this integral accounts for the deflection of particles or droplets under the effect of impingement of gas molecules. And I have not, in this first equation, I have not I've not taken into account collisions between particles or droplets in the dispersed phase. it could be done, but for the simplicity, for the sake of simplicity, I'm not going to do that in this talk. And the second equation is a kinetic equation for the propellant, therefore for the gas. So here you see on the left-hand side the advection operator driving the inertial motion of the gas molecules. On the right-hand side, you see the Boltzmann collision integral. So this one takes into account collision between gas molecules, as usual in the kinetic theory of gases by Boltzmann and Maxwell. And there's an additional term which takes into account the friction on gas molecules. So it's the, if you want, it's the slowing down of gas molecules resulting from collisions with the dispersed phase. And in front of each of these collision terms, I have put the usual scaling factor by analogy with the case of the Boltzmann collision integral, which is well known and can be, for instance, read in the last volume of the course of theoretical physics by Landau and Lifshitz, volume 10, I believe, in kinetic theory. So each of these prefactors involve these average cross sections, which have been already described in the table of parameters. Now, the scaling assumptions under which the Vlasov-Navier-Stokes equation, Vlasov-Navier-Stokes scaling system is going to be derived, is that, as I said, first epsilon and eta. So epsilon is the thermal speed ratio, Vp over Vg of the particles to the gas. So this is going to be a small parameter, and eta is the mass ratio. So it's also equal to Np over Ng, right? And it's going to be assumed, and this is a key assumption, that eta is much smaller than epsilon to the square. So there's an ordering between these two parameters, they're not independent, sense that eta has to be much smaller than epsilon square. And in the first line of the scaling assumption, you see that in addition to the definition of epsilon, I'm also adding the fact that the first, this second equation actually in the first line tells you that the mean free path of gas molecules between two collisions with droplets or particles, or heavy particles, this is going to be actually large, whereas the second, or actually the third equality here tells us that the mean free path corresponding to molecular collisions is going to be much smaller than the length scale of the flow. Right, with that system of assumptions here, you arrive at the following form of the scale Boltzmann system: d by dt of f plus v grad x f plus 1 over eta, the deflection integral capital F little f. So that's for the dispersed phase. And the second one for the propellant is d by dt of little f plus 1 over epsilon w grad x little f equals to the friction integral r of little f and capital F plus 1 over epsilon square, the Boltzmann collision integral on little f. And here you see immediately that because of the 1 over epsilon squared in the second equation, the gas distribution function is going to be at equilibrium to leading order. So it's going to be m of w, where m of w is a centered Maxwellian, right? So which in dimensionless variables is simply a center reduced Gaussian, and there's going to be a fluctuation of the gas distribution function around this Maxwellian, which will be henceforth denoted by G. And of course here, for convenience in this scale Boltzmann system, although I'm dealing with dimensionless variables, I've dropped the hats on the scale quantities and all the unknowns in this system, and now I'm working with this system. All right, so with that, here is the formula for the Boltzmann collision integral. So I remind you that this is the rate of change in the gas distribution function due to collision between the molecules. So typically at the velocity w, here you enrich the population at the velocity w as a result of collisions with involving a particle with a velocity w prime and a particle with velocity w prime star before the collision, and you produce out of this one particle with velocity w, and so there's a loss term which corresponds to the depletion of the population at the velocity v due to encounters with molecules with other velocities, and which the velocity w will change. And there's a collision kernel here, for which I've taken this particular form here. So this collision kernel involves just the absolute value of the cosine of the relative velocity with respect to this unit vector omega, which I'm going to define in a minute. This special assumption refers to as the pseudo-Maxwellian collision kernel. It's a special kind of molecular interaction, and this function c is normalized by this condition here, and the system of equations defining w prime and w prime star here in terms of w, w star, and omega are they describe the most general formula, the most general transition starting from a pair of velocities w and w star and producing velocities w prime and w prime star, for which the conservation of momentum and the conservation of kinetic energy is guaranteed. So in other words, geometrically, if you put yourself in the frame, in the center of mass reference frame, typically geometrically this transformation from w star to w prime and w prime star can be read as a reflection, or as a symmetry if you want, where the relative velocity pre or post collision w minus w star is transformed into w prime minus w prime star, and omega is the exterior angle bisector of the two relative velocities. So you have conservation of the kinetic energy, obviously, because in this picture here, which is in the center of mass reference frame, the length of the relative velocity is invariant during that collision. All right, so that's the theory of the Boltzmann collision integral for point particles and elastic collisions. Now, let me come to the description of what is specific in the case of these aerosol models, which is the deflection and the friction operators. So these are integrals similar to the Boltzmann collision integral, and the formulas for the D and R are given on the slide. So they're pretty much formulas completely analogous to the ones for the Boltzmann collision integral, the Boltzmann-Maxwell collision integral, which is well known in the kinetic theory of gases, except there are two slight differences in this case. Whereas first, the deflection and the friction integral, instead of being quadratic in either little f or capital F, it always involves a multiplication of little f evaluated at some velocity by capital F evaluated at another velocity, right? So that's a first difference. A second difference is that if you look carefully at the collision relations, namely the V double prime, W double prime in terms of V and W, you will notice that the formulas for this transformation are slightly different in that they involve the ratio 2 eta over 1 plus eta, or 2 divided by 1 plus eta, which has to do with the fact that the masses of the molecules and the particles or droplets in the dispersed phase are different. So typically this ratio eta over 1 plus eta would it comes from the reduced mass in such collisions. And there's also the fact that in the first equation, V is measured. So in the first equation, W is measured in the scale of V. So that's the reason why there's a 1 over epsilon that appears in front of the W. I remind you that the scale of W is the thermal velocity of gas molecules, which is much faster than that of particles. And conversely, in the second equation, then V is scaled with epsilon because the thermal speed of particles in the dispersed phase is much smaller than in the gas. And finally, there is this assumption on the collision kernel, which is a function of B of Z and omega, which depends only on the relative speed and the cosine of the angle between omega and the relative speed, which appears in these formulas, right? And you have these relations here that B grows most linearly in the relative speed, and that if you integrate it in angle, it's bounded below by a function of the norm of z divided by 1 plus the norm of z. So typically these inequalities correspond to the grad, so-called grad cutoff assumption, ruling out grazing collisions at this scale. But I will return to grazing collision in a minute. However, here, these formulas, they refer to elastic collisions between particles with different masses. And you might think that, in fact, the collisions between the gas molecules and the particles in the dispersed phase don't have to be elastic at all. And in fact, there's an inelastic collision model, which I want to say a few words now, because indeed you can think of these particles or droplets as being macroscopic objects, and that there's going to be a diffuse reflection of gas molecules at the surface of such a particle, which occurs with a surface temperature which is given, right? And so here on this slide, I have a blue large particle moving at a velocity capital V, blue velocity, and here I have a small molecule impinging on the particle at a velocity capital W, red, and being diffusely reflected. And here you have the several possibilities of reflected molecules after the interaction. So such inelastic collision model has been written by Frédéric Charles in a PhD thesis almost 10 years ago. And here are the formulas for these deflection and friction operators in this case. So you see, I may just comment on the differences with the elastic case. First, you need to describe these integrals. You need two different inelastic kernels, KPG and KGP. And for each of these kernels, for example, KPG, essentially you assume that you have the velocity capital U of a gas molecule, and this KPG is going to be like a scattering operator modeling, describing the transfer from pre or post collision capital V to little v. So here this is, so capital V will be the pre-collision and little v the post-collision, and here it's the reverse, right? So here little v is the pre-collision, capital V is the post-collision, right? And you have a similar expression for the friction operator. And here are the formulas for these inelastic kernels. So they involve the surface temperature on the droplets through this square root of mg divided by the Boltzmann constant times the surface temperature, which I call beta. And because I'm having a diffuse reflection with Maxwellian remission function. So here these two kernels involve this Gaussian factor, and here there is this parameter lambda, which is the analog of the reduced mass and the ratio of the thermal speed as were introduced in the elastic model, essentially. Right, so this is the model for these inelastic collisions, and with that, here is, if you want, the theorem that summarizes the formal Vlasov-Navier-Stokes limit from this Boltzmann system to the Vlasov-Navier-Stokes system. So assume that you have a sequence of solution to the scale-Boltzmann system which satisfy the scaling assumption. So I have a sequence of parameters eta, a sequence of parameters epsilon, eta n, epsilon n, that satisfy these scaling assumption, eta n small compared to epsilon n squared. And I have the solution capital Fn and little fn, which I remind you is going to be a small deviation of the centered reduced Maxwellian capital M. And if you assume that capital F and little g converge to limits capital F and little g, satisfying these assumptions, these bounds, typically uniform bounds in A and B, then the limit capital F and the velocity field, which is built on the fluctuation of number density or fluctuation of the distribution function in the propellant, will be the things that satisfy the Vlasov-Navier-Stokes system. And here, the friction rate kappa, I will give the formula of it below in the next slide. But at the moment, because I'm dealing with a gas which satisfies, which is a gas of Maxwellian molecules, then the friction, the kinematic viscosity of the gas is given in terms of the collision kernel and the Boltzmann equation, that is the function c of mu, where mu is the cosine of the angle of the relative velocity with the unit vector omega modeling the collision. It's given by this formula here, which is roughly the dimensionless. It's analogous to the dimensionless variant of the formula that you can find in classical textbooks such as Chaban-Colling, for instance. Now, for the friction rate kappa, well, the fact is that if you look at the deflection operator scaled by the parameter eta, which appears in the first Boltzmann equation of the Boltzmann system, this binary Boltzmann system, this is the term which produces the drag acceleration described in the which appears in the Vlasov part of the Vlasov-Navier-Stokes system, and this kappa is given by the two expressions here. So in the elastic case, kappa is given by this integral, which involves the collision kernel capital B that appears in the integral operator D. And in the inelastic case, well, you have a much simpler expression, which involves the temperature through this parameter beta, which appears in the denominator of the first term here. Briefly, the reason why such behavior, such an asymptotic behavior occurs, is that if you consider, for instance, the elastic case, then you see that if you integrate the deflection term against a test function, smooth test function phi of v, say, and if you use the collision symmetries, you can essentially have the capital F of v and the little f of w, which are invariant under the collisions, and then the transformation is transferred to the test function v, and then this j integral becomes the integral with respect to capital F of v, little f of w of the observable quantity, which involves the difference between f of v and phi of v and phi of v double prime. And now, if you remember the formula for v double prime, you see that v double prime is in fact very close to v because eta is very small. It's the smallest of all the two small parameters involved in the problem. And there you Taylor expand this difference here, and that produces a gradient of phi. And the gradient of phi, when you integrate by parts, again, will essentially account for this transformation by which this limit by which this collision integral here is transformed into a divergence in v of this drag force written there, right? So this is essentially the key idea which explains how the Vlasov equation arises asymptotically from the first Boltzmann equation in this binary system. Let me now conclude with a few words about the possible extension and the open problems remaining in this class of problem. So, I've only discussed here the Vlasov-Navier-Stokes limit of this coupled Boltzmann system, but in fact you could also derive in the same way Vlasov-Stokes system, where for slower propellants, the equation for the gas would be a Stokes equation coupled instantaneously to the dynamic of the gas. So in other words, you neglect the inertia in the Navier-Stokes equation. You can also take into account compressibility in the propellant. Of course, this is not done here, and this is the reason why you have an incompressible flow at the level of the Navier-Stokes equation. You can also take into account dispersed phase collisions. As I said, you can take Pauli dispersion. That is, you can have droplets or particles which are not of the same size, but distributed in size. One of the advantages of this kinetic modeling is that you have access to a richer description of the drag force than the simple Stokes formula for a flow past a sphere, which you can find in the Landau, Lifshitz, and all classical textbooks in classical mechanics. And I want to, in particular, to direct you at a detailed description of rarefied flows past a sphere, which has been done by the Kyoto School in kinetic theory, namely the team of Professor Sone and Professor Aoki, Professor Takata, and was recently a very nice paper by Professor Takushi from Kyoto in Journal of Fluid Mechanics 3 years ago. And well, finally, this one of the items in this derivation involves, of course, derivation of the fluid equation from the Boltzmann equation. So formal derivations have been known for quite a long time. The first derivation of the Navier-Stokes equation for incompressible flows in the low Mach number limit, I think, is a paper by Yoshio Sone, which appeared 50 years ago almost in the proceedings of RGD meeting. And I've written some more references here. In fact, you can also have rigorous derivations in the sense that you don't have to assume the convergence of the distribution function, but you can actually prove this convergence. These rigorous derivations are much more difficult, but they are now rather well understood. And I put some two references here, and you can look at these two papers and the reference therein to get more information on this topic. With that, I close, and I wish the Japan Society of Fluid Mechanics a very happy 50th birthday. Thank you.
All right, François, thank you very much for your talk. Let me just set up here. All right, so for those of you watching, we are now in the fourth and final talk of the Unofficial Japan Society for Fluid Mechanics 50th anniversary meeting held here in Osaka in the middle of a Typhoon Jebi. So we have one question that came out that was posted on the YouTube website, and I'm going to answer the questions after all of us have given talks, which means I'm the next speaker. So let me get my talk ready, and so 1 second here while we get started. Sorry about this. So, for those of you who are not in Osaka, let me just tell you that during the last hour or so, we had such strong wind gusts that the building that we are in was literally swaying and making us feel seasick. So this was a real, quite a real event, and it was appropriate that the physical meeting was indeed cancelled. All right, so let me get ready to present my own talk. All right, so I'm the last speaker. My name is Nigel Goldenfeld. I'm from the University of Illinois at Urbana-Champaign, and I'd like to begin by thanking the organizers for inviting me to talk on this auspicious occasion, 50 years of the Japanese Society of Fluid Mechanics. It's a wonderful accomplishment and many great scientific contributions, as was noted at the beginning of the session. So the last two talks that were scheduled for the program, actually the last three, were theoretical talks, and Professor Stone from Princeton had obligations and was unable to come here due to the delays caused by the hurricane. Professor Uriel Frisch has posted his slides on the website, and I do encourage you to look at them because they report some beautiful recent advances on the Osaka conjecture to do with the dissipation anomaly and the Euler equations. Now, what I'm going to talk about is something different from that, and that is a very old problem that goes back more than 100 years, of course, which is the laminar-turbulence transition in pipe flow. And the reason that I'm going to be talking about this topic is because during the last 10, 15 years, this has really seen enormous progress as a result of remarkable experimental advances and some theoretical contributions from a variety of different sources. What I'm going to talk about is our work which is trying to understand the behavior of the transition from the perspective of statistical mechanics, which I realize is not a topic that is perhaps well appreciated in the fluid mechanics community, but I think it will become so, as you'll see during the talk. So the work I'm going to talk about was done with Hongyan Shi and Songlin Shi, and we were supported in part by the National Science Foundation, and the references are given below. So we're very used to the idea the idea that kinetic theory can give rise to fluid mechanics descriptions. In fact, we heard a lot about that in the previous talk. So the deterministic classical mechanics of many particles in a box gives rise to a statistical mechanics. And indeed, this is a very common programming exercise given to students in statistical physics in their final undergraduate year. And one can very easily see from molecular dynamics simulations how the Boltzmann distribution and so on emerges. Now, what happens when we have an infinite number of particles in a box? So that, of course, is now a field, and it's described by the Navier-Stokes equations for a fluid. And indeed, this also gives rise to a description which is can be understood using statistical mechanics. So the idea that one can have a stochastic and indeed weak solutions from a deterministic equation is of course not new, but we're going to see in the laminar turbulence transition especially that this perspective gives unique predictions that in fact I'll show you have been verified experimentally. So going right back to the beginning, we have Reynolds in 1883 reporting on the turbulence transition, and he shown the apparatus is shown here. There's an inlet, and then the fluid comes out the other end in this pipe, and of course, as you increase the speed of the fluid, it goes from smooth and regular and predictable and laminar to eventually a jagged, irregular, stochastic turbulent flow. But in the middle is this transitional region where he noted straight away that it doesn't appear, the turbulent phase doesn't appear all at once in all parts of space, but indeed occurs in some regions of space and then not in others. And he called these regions flashes of turbulence interspersed by laminar regions. Today we call these flashes puffs, but his observation was essentially correct, and he also gave a rough figure for the transition, about 2000, which indeed is something that is supported by modern experiments. Now, the modern experiments that I want to focus on in this talk are really the work of primarily the work of Björn Hoff and his group, and the experiments that have really revolutionized the field are ones that were reported in Physical Review Letters about 10 years or so ago. Now, the idea in these experiments is to get very detailed statistical information, and so the idea here is that you have a pipe, and the fluid is going through it in a laminar state, and you inject a small disturbance at some distance from the outlet, and you ask what happens to that disturbance. And if you inject the disturbance appropriately, it creates a small puff of turbulence, and that turbulence will then live for some lifetime and may indeed live long enough that it actually advects to the end of the pipe, or it may decay before it gets there. And if it gets to the end of the pipe and it doesn't decay, then the velocity at the end is lower, and so the fluid comes out following the orange trajectory, the red trajectory. If the puff is already decayed, it is going faster, and it follows the yellow trajectory. And so you can get a series of binary pieces of data that tell you, did the puff survive until it gets to the end of the pipe? Yes or no. You can vary the distance from the disturbance to the outlet, and so you can do time of flight. And so what that means is that if you do very many repetitions of this in a very well controlled temperature control apparatus, very carefully engineered, you can measure the survival probability for a turbulent puff as a function of time and as a function of Reynolds number. So let's have a look then at what we see when you do these experiments. So here is the phase diagram of turbulence, the Reynolds number on the horizontal axis, around about between something like 1775 to around 2050, you have metastable puffs. So shown up here at the top is a picture of the visualization of the turbulent intensity as a function of space, and you see a puff here, which is in fact going to decay. It will not live forever. It has a finite lifetime. And if you measure the probability of it surviving, you find that it goes as an exponential in time. So here in the bottom is the probability as a function of Reynolds number and time, and on a log scale on the vertical axis, on a linear scale as on the horizontal axis for different Reynolds numbers. And you can see that these data fall on a series of straight lines, and so that means that you can extract the lifetime tau as a function of Reynolds number. And when you measure that, what you find is shown here on the curve on the right. Now, it's hard to read perhaps, but the vertical axis is the logarithm of the lifetime, and the horizontal axis is just the Reynolds number. So in fact, what this is showing you is that if it was a exponential function of Reynolds number, these curves would be a straight line on this plot. But in fact, you can see that the puff lifetime is an increasing function of Reynolds number that increases faster than a straight line. And that means that it's a super exponential function. Now, moving on to higher Reynolds numbers, above about 2050 or so, what happens is that if you start off with a puff, it will not just decay, it will actually split into two puffs, and then those two puffs will behave independently. And what they will either decay or themselves will split. And you might imagine that the higher the Reynolds number, the shorter the lifetime of the puff before it splits. In other words, as you take a puff, as you increase the Reynolds number, it'll very quickly split into two. As you go to lower and lower Reynolds numbers, the time that it takes before it splits is going to get longer and longer. So if you now plot the splitting probability as a function of lifetime, as a function of time for different Reynolds numbers, again you get an exponential behavior. Again, you can read up off the lifetime. This is essentially the mean time between splitting events, and that's the curve shown on the right here in blue, and you can see that that is also a curve curving upwards on this logarithmic linear plot, which means that both these lifetimes scale as a function of Reynolds number to within measurable uncertainties, well fitted by a super exponential function. Now, what is plotted on the left-hand side is double log, and on the right hand, on the bottom, the Reynolds number. So what we've learned from these experiments is that all the turbulent lifetimes, the timescales that characterize turbulence very close to the transition, behave or can be well described as a super exponential scaling, e to the Reynolds number. Now, this is not just a fanciful functional form. As we'll see later, if I have time, we'll see that this actually has a theoretical interpretation and can be predicted. So what I want to talk about now is how we can understand the metastable turbulent puffs, and we can understand the spatial temporal intermittency. And what we're going to see, in fact, is that the behavior near this transition to turbulence, even though we don't see any critical Reynolds number in the graphs that I previously showed you, we will in fact find that there is a critical Reynolds number, and in fact that the transition is a second order phase transition. So now I've talked about phase transitions, so let me remind you of how we model phase transitions in statistical mechanics, because there's a lot of misconceptions there. Even though the Nobel Prize was won by the leading figure who solved the problem of phase transitions, the accepted theory, the renormalization group theory, that was Ken Wilson. Even though that work is now the foundation of condensed matter physics and statistical mechanics, the way that it works is not so simple to explain as one might think. So let's see how it works. The typical system that was most well studied by statistical physicists is a magnet, and a magnet, of course, is an outcome of the electronic degrees of freedom in a material. Now, what one does is one starts off with the electronic band structure and the quantum orbitals and the interactions of the spins and so on. But that problem is too hard to solve analytically or even sometimes numerically. So one makes a simpler model called the Ising model, which is simply a model of dipole moments, spins, which are quantum mechanical and which interact. And that model is not really derived systematically from the electronic structure. It's more or less understood in the heuristic way from the overlap of quantum orbitals. But that model is quantum mechanical, and it's still too hard to solve in general. So one then tries to make the spins classical and just removes all the quantum commutation relations and makes this thing classical. Now, the classical model of three-dimensional magnetic spins is also too hard to solve analytically. It can be solved in 2 dimensions, and Onzaga, in fact, was the person who succeeded in that tour de force in 1944. But other than that, we can't solve this model exactly, although we can solve it numerically. But what we can do is we can do what is called Landau theory, which is we can look at the symmetries of this model of spins on the lattice, and the symmetries already tell us how one can write down an effective free energy for this complicated material, and that free energy is called the Landau theory. It's typically a kind of power series expansion in the free energy as a function of the magnetization as a function of space. And then from that Landau theory, one then uses the renormalization group to compute the critical behavior very close to the transition. Now, what's amazing about this, I'm not going to show the data for it, but the renormalization group theory makes absolutely precise predictions for critical exponents and how, if you plot the data in a certain way, the data for, say, the magnetization is a function of temperature and external magnetic field will all collapse onto one universal curve. The theory predicts that universal curve with no adjustable parameters. The data, when you measure them, fall exactly onto that curve. It's absolutely remarkable that a theory makes such precise predictions, but it's even more remarkable when you realize that each of the steps in this logic here, from electronic structure to Ising model, to classical Ising model, to Landau theory, and then Landau to renormalization group, the actual ending up theory is a model of a model of a model of a model of a model. And yet, all of those heuristic, unsystematic approximations end up giving you an exact result, which agrees very well with experiment. And how that happens is not something I can tell you in this talk, but it is true. And if you're really interested, I can recommend a very good book on renormalization group and phase transitions if you want to learn more about this. But it's really quite remarkable. Now, turning to turbulence, we can start off at the lowest level of description, not with electrons in the material, but the kinetic theory. And the kinetic theory then can be coarse-grained up to a very good representation of all fluid flow, the Navier-Stokes equations. Now, the question that we're interested in is what happens at the laminar-turbulence transition. That's like the phase transition between a paramagnet, a non-magnetic material, and a magnetic material as you change the temperature. So the question that we're going to ask in this talk is what is the analog of this effective theory, the effective free energy for a magnet very close to the transition, and then what is the analog of the renormalization group universality class of the transition. In other words, what is the precise description of the behavior of the lifetime and the other properties of turbulence, the turbulent fraction, for example, as you get very close to the critical Reynolds number. And we're going to see that we can actually solve this problem. Now, how do we solve it? The way we solve it is to realize that in condensed matter and statistical physics, every step of the logic requires using symmetry, but it also requires understanding what are the important modes near a phase transition. Now, we know on general grounds that phase transitions are generally controlled by long wavelength and collective emergent modes, and we're going to ask the following question here. In the Navier-Stokes equations, very close to the transition, what are the important collective modes that are the ones that need to be represented very close to the transition? In other words, near phase transitions, dynamics simplifies. And we want to ask, what are the simplifications that happen when you get close to that transition? Now, we can't do any technical approximations, any power series expansions or other systematics, because there's no small parameter in this problem. Just like there's no small parameter in the phase transition problem, and that's what made it so hard that when it was eventually solved, the person who solved it was awarded the Nobel Prize. So what we're going to do instead is we're going to use direct numerical simulations of the Navier-Stokes equations. So what I'm showing you on this slide is the simulations that were done using Ashley Willis's excellent code, Open Pipe Flow. And what we did was we simulated in a pipe geometry the flow of turbulence in the regime close to the critical Reynolds number. Now, what we observed after much experimentation and so on, which I can't go into right now, what we observed was two important modes. The first is the small-scale turbulence, which I'm showing you here schematically in green, but the other was a surprise. The other mode that we saw was a mode that is azimuthal. It's perpendicular to the pressure gradient across the pipe, and it's shown here in the movie on the lower right. It's a mode that is a k = 0 mode. It has no z dependence, but it does, and it has no azimuthal dependence, but it does have radial dependence and time dependence, and that's shown in the movie. Now, when you measure the energy in this mode and the energy in the turbulence, what you find is shown in the figure on the left. The green is the turbulence, the blue is the zonal flow as a function of time. And for the precise definitions of how we filtered the solutions and measured these things, I'm afraid you have to look at the original paper. Now, this mode, the blue mode, we call it a zonal flow. It's a zonal flow just like in geophysical flows, and it's powered not by the pressure gradient across the pipe, but in fact draws its energy, as I'll show you in the next slide, from the turbulence itself. So it's an emergent and collective mode. But what you see here is that the green and the blue curves, they're oscillatory, but they're slightly out of phase. And that out of phase suggests, we've seen this before, this suggests that they actually behave like predator-prey oscillations in an ecosystem. And you'll see why I say that on the next slide. So here we are looking at the zonal flow. So again, the turbulence is small scale, so k greater than 0. The zonal flow is large scale, a k = 0, m = 0 mode, induced by the turbulence. Now, the important thing about it is when you try to understand where this mode comes from by looking at the Reynolds momentum equation, what you learn is the following: that the azimuthal velocity is driven by the radial gradient of the Reynolds stress fluctuations shown here, and then there's some decay term. But this is the term to concentrate on. What happens here is that the anisotropy in the turbulent fluctuations at small scales creates a Reynolds stress, and that Reynolds stress generates the mean velocity in the azimuthal direction perpendicular to the mean flow that is driving the turbulence induced by the pressure drop. Now, what happens is that as the zonal flow moves radially like this, it shears the turbulence and therefore makes it less anisotropic. In other words, it makes it isotropic. Now, but it's the anisotropy that is the source of the azimuthal flow, and so the turbulence generates the azimuthal flow, but the azimuthal flow destroys the turbulence, and that's why we say it's like a predator-prey relationship. How do I know that this equation is correct? Well, we measured the left-hand side and we measured the right-hand side as a function of space and time, and that's shown over here. So this is the in blue is the Reynolds stress spatial derivative at fixed time. In gray is the time derivative of the azimuthal flow, and then here on the right, we've plotted now the same two quantities, but now at fixed radius as a function of time. And you can see that these curves fall very well very close to each other, showing that in fact the two terms in this equation are indeed proportional to each other. So what I've just told you and shown you is that the turbulence induces a zonal flow. The zonal flow suppresses the turbulence. Once the turbulence has gone down, then the zonal flow itself goes down. And once the zonal flow has gone down, that's the term that suppresses the turbulence. So now the turbulence can go up again. And that's just exactly what happens in an ecosystem where you have a prey, let's say a sheep, a predator that is a wolf. The presence of the prey gives the wolves plenty of food to eat. The food that they eat is the sheep. The sheep population then goes down, and then without any food, the predator population goes down, and the cycle begins again. And this is the typical predator-prey oscillations that you see in ecology. Okay, now what does this have to do with turbulence? So what I've shown you then is that if I look now, if I take that seriously, what we've just seen is that the important modes near the transition are a zonal flow and small-scale turbulence. So let's now write down all the possible diagrams that represent triads of interactions between this collective mode and the small-scale turbulence. And it's easy to write them down, and they're shown here on the left. So the lines represent the zonal flow, the wiggly lines represent the turbulence, and these in fact are formally Feynman diagrams that you would write down in the wild expansion of the Navier-Stokes equation. Now, remember we talked about this as having a predator-prey type analogy. So this analogy is absolutely mathematically rigorous. So let's suppose that I denote by A, the predator, B, the prey, and E, the food that they live on. Over here I have the zonal flow, the turbulence, and then the empty state, is just the laminar flow. So let's have a look at what these equations mean. So here, let's have a look at this one. So so this one says the following: I have a zonal flow, a turbulent mode splitting into two wiggly lines, two turbulent flows. Over here, the turbulence is like the prey, because it is the one that is suppressed by the zonal flow. So this equation then says I start off with a single prey, that's B, and plus nothing, that's E, the empty site, and with some rate B, that produces two new prey. This is in the biological analog. This is a sheep eats some food, has enough energy to then replicate and make two sheep. Here's another one. This one's perhaps easier to understand. So here is a zonal flow. Here is turbulence, and it interacts to produce another zonal flow. So this is in fact A, the predator, plus B, this mode here is one where they meet and then actually produce two solid lines. That's two zonal flows. So you get A plus B goes to A plus A, and so on. So there's a formal analogy between these flow diagrams, the Feynman diagrams for the flow, and the predator-prey ecosystem. And these are stochastic differential equations. All right, so now what I'm going to show you is that the phase diagram of pipe flow turbulence and the phase diagram of this stochastic ecology model that represents the important modes of Navier-Stokes equations very close to the transition. I'm going to show you that we can replicate now everything I showed you from the experiments. So this here on the top is the phase diagram that you've seen before of pipe flow turbulence. Here at the bottom is the phase diagram of the predator-prey model, plotted not as a function of Reynolds number, but as a function of the birth rate of the prey. The more the prey create babies, then the more prey there will be, and then the more the ecosystem can function. When you work out the phase diagram of this through computer simulations and mathematical analysis, you find that, look at it in space, there's a region where you have a metastable population. Whereas if you start off with a population of prey, they don't have a high enough birth rate. So what happens is the predators, the wolves, eat them, and eventually they die away. That's shown here in this figure at the bottom. But as you increase the prey birth rate, then of course they are able to make enough babies at the same time as they're being eaten by the predators, by the wolves, and so the population can persist. And in fact, what you'll see is that you have, if you made up a little localized region of prey, it will eventually split into traveling waves, just like the puffs in turbulence split up here. Now, when you look at the linear stability of the mean field solutions of these predator-prey equations, what you find is that this state here is actually absolutely stable, and all the linear eigenvalues about this state are real. But as you increase the birth rate, these modes acquire a complex conjugate part, and so you go to a stable spiral rather than a stable node. And this spiral here then gives you oscillations in space and time, which correspond to these traveling fronts and these puff splitting events. And we can see that here by drawing the world lines of these systems. So these are data from Avila et al. In Science 2011. These are experiments and simulations of puff splitting and pipe flow turbulence. And on the horizontal axis is space, the color scale is turbulent intensity, and time goes up the vertical axis. What you're seeing here is the trajectory of a puff that at this time here suddenly splits into two, and now you've got two puffs going in this direction, and then this puff splits again, and so on and so forth. Similarly, over here in the predator-prey ecosystem, you start off with a prey, and then it splits and splits and splits, and you get this complicated space-time pattern of intermittency in both space and in time. So both the predator-prey system and the turbulence system on the right have the same phenomenology. That phenomenology extends even to the lifetime. So if you go and now do the same types of measurement that Björn Hoff's group did on the turbulent puff lifetime, but now you do it on the predator-prey ecosystem model, then you find the following thing: the lifetime of the patches of prey as a function not of Reynolds number, but of their birth rate, increases super exponentially. And you can see it increases super exponentially because this is the logarithm of the lifetime as a function of the birth rate, and this curve is curving upwards, just like the curve over here for the turbulent puff to K rate curves upwards. Similarly, the splitting occurs as in the spatial temporal regime I showed you before, and again the lifetime, the mean time between population splitting events also curves upwards, indicating super exponential behavior, just as you see in the turbulence experiments. So what we've learned is that the transition from turbulence to laminar is exactly the same as the transition in the ecosystem from a coexistence of predator and prey, the coexistence, to the state where everything goes extinct. The extinction in ecology is like the death of turbulence, and they both obey super exponential scaling very close to the onset of their transition. So what I've shown you so far is that we start off with classical turbulence. We don't make any approximations, we just do direct numerical simulations of Navier-Stokes. And what we find is that very close to the transition, the Navier-Stokes equations are really governed by a kind of two-fluid model, this large-scale zonal flow and the small-scale turbulence, and we saw that they behaved like a predator and prey in an ecosystem with stochastic pi/2 out-of-phase population oscillations, and those population oscillations gave rise to super exponential lifetime scaling, just as you see in the experiment. Now, the question we really want to understand is, if I start from classical turbulence, what is the nature of the laminar turbulent phase transition? Okay, now I'm going to show you that that transition is in fact a statistical mechanical model called directed percolation, and I'm now going to show you in the last part of the talk how the predator-prey model produces this model of directed percolation. And it's a very strange model and very counterintuitive that a continuum fluid mechanics problem agrees with the behavior predicted by a model of particles hopping on a lattice, which is directed percolation. So let me tell you what directed percolation is. So the way I like to think of this is what happens in the morning when you pour water on the coffee granules in your coffee filter to make your morning coffee. So if you drip the water down onto the granules, if the granules are packed too closely together, the water can't percolate through the coffee granules and will in fact back up and eventually overflow and make a mess in your kitchen. If, on the other hand, the coffee granules are not packed together too closely, the water can percolate through. And if they are just right, the water will percolate through, and it will take the longest time to percolate through, and you'll get the most tasty cup of coffee. So what does this have to do with turbulence? So over here on the left, I've shown you a picture of that process. So the red sites on this lattice you can think of as the paths that water takes in your coffee filter. Now, what Yves Pommeau realized in 1986, in the end of a very influential paper, was that turbulence could behave like directed percolation. And the reason is this: if you have a small patch of turbulence, it can indeed very quickly relaminarize and go into the laminar state, and then it stays there forever. But turbulence can also spread spatially and contaminate its neighborhood. And that's exactly what directed percolation does, because you can see here the red, this is time going down and space horizontal. What's happening is the water is finding a percolation path through here, so it is spreading, and then at this point here it doesn't spread anymore, so then it has literally gone into the non-spreading state, and now no spreading is possible after you've got beyond this point over here. Now, if you look at the trajectories here, you can see that every trajectory in this graph can be composed of 4 different types of trajectory. So here on the top row, that's time t, and then this is at time t plus delta t, what the time evolution of the system is. Here is a filled site going to an empty site. So it starts off occupied with fluid, and then the next time step, it disappears, it stops flowing. Here in the second line, what happens, you have decoagulation. Start off filled, and then the next time step, both the lattice sites below are occupied. Here starts off over here and moves diagonally, that's diffusion, and this is coagulation. 2 lattice sites that are close together merge into one, and that's coagulation. Every trajectory that you can see in directed percolation is composed of these 4 motifs linked in random ways. Now, what happens is, as I explained with my coffee filter analogy, there's a certain probability that the water can percolate through. That percolation probability is called little p. For small p, if it's not able to get through, the coffee grains are packed too tight, the flow stops very quickly after it started. On the other hand, if it's very easy for the water to flow through, it very quickly finds a path through and flows down from the beginning down to the end. And then there's the magic point where the coffee tastes the best, where the water flows through, it just manages to get through to the other side, spends the longest time in the flow path in the middle here. Now this, if you measure the as a function of p, how many sites are occupied at long times, that's called the density rho, and in turbulence we would call it the turbulent fraction, and that scales as a power law of p minus this critical p value. Similarly, there are diverging correlation lengths describing the growth of length scales that's common in phase transitions. Okay, so now if you go and measure the lifetime in directed percolation, and again, I'm not going to have time to go into exactly how one does that, one finds that the longest percolation path and the longest length of empty sites, those represent the puff decay and puff splitting statistics, and those for different system sizes behave super exponentially as shown here, just as is seen in the turbulent lifetime. So what we learned from this is that this model of directed percolation that Yves Pommeau guessed might have something to do with turbulence, if you just simulate it in 3 space and 1 time dimension, actually does indeed have this super exponential statistics. So now we've learned something very surprising. We've learned that near the laminar turbulent transition, there's 2 important modes that behave like the predator and prey, the zonal flow and the turbulence. On the other hand, I just showed you that near the laminar turbulent transition, lifetime statistics grow super exponentially with Reynolds number, both for the predator-prey model and now for directed percolation. Now the question is, how can both descriptions be valid? And that's what I'm going to show you next. Now, so here, the real way to prove this is using statistical field theory and quantum field theory techniques, but you can see it very simply in a graphical way. On the left, I've written down the equations describing predator-prey, but now I've allowed them to actually hop around on the lattice, so they live in space. So both the wolves and the sheep, the predator and the prey, can diffuse. The A is the predator, the B is the prey, the E is the empty sites or the food. These are all the equations. Trust me, these are the ones that we saw before. Near the transition to prey extinction, the prey population is very small and the predators can't survive. So we'll just simply set their density, their number equal to 0, and cross out those terms. So now we have just these equations left. In ecology terms, we've gone from a 3 trophic level ecosystem with predator, prey, and food to one with just prey and food, very close to the transition. And now if you look at the remaining equations we have left, each of these equations has a graphical interpretation which has all the 4 basic motifs that I showed you for directed percolation. So what I've just showed you then is that near the extinction transition, stochastic predator-prey dynamics reduces to directed percolation. So what I've now summarized then is that we started off with direct numerical simulations of Navier-Stokes. We found that there was a 2-fluid model, zonal flow and turbulence, behaved like predator-prey. That predator-prey statistical mechanical model not only replicates the phenomenology that you see in the experiments, but then predict that the behavior should be in the class of this theoretical physics model called directed percolation. Is it true? Now I want to show you, just to end, the experimental evidence for this in a transitional turbulence in different flow geometries. Now, what you need to know is that once we know the universality class, as statistical physicists call it, that this is directed percolation, the critical behavior, the way that the turbulent fraction behaves near the onset, is precisely known and is precisely specified by the theory and can be calculated. So we know that certain quantities behave with certain power laws, and those power laws are known to 7 or 8 decimal places. This was a brilliant experiment, another one that was done by Björn Hoff's group, reported in Nature Physics 2016 in the same issue that our theoretical work appeared. This was a Couette system, but a Couette system where the distance in this direction is very small compared to the radius, and also the spacing between the plates is very small. So this is a very, very high aspect ratio Couette system, almost plain Couette. What's important is that the outer cylinder is rotating and the inner one is stationary. That means that this system has a subcritical transition from laminar to turbulence, just like pipe flow does. If you look at the system on the outside, as it is spinning around, it produces turbulent patches, which are these black marks that you see here in these photographs. And they spin around one rotation, second rotation, third rotation. You're just looking over here and watching the flow and then unwrapping it like this. So now you're seeing the position of these turbulent stripes on successive rotations. Take those successive rotations and put them underneath one another, and then you get a space-time picture of where the turbulent regions are, shown in blue here. And for less than the critical Reynolds number, you see a picture like this on the left. For greater than the critical Reynolds number, you see a picture like this on the right, and in the middle you see a picture like this. And these pictures, as you'll see with your naked eye, are just very much like the pictures you see from directed percolation that I showed you before. You see the same thing, by the way, in ecology. Here we start off with our predator-prey system written down in a strip, and then as you plot out the space-time statistics, again it maps out this directed percolation type of picture, just as the simple algebra, the mathematics I showed you previously suggests. So we can also, and again in those experiments, I don't have the picture here, but you can measure the onset of turbulence, the turbulent fraction, and it agrees quantitatively with the predictions. There's other data that was taken on this, not just in Couette, but also in plane channel flow by Professor Asano's lab in the University of Tokyo. And again, in that two-dimensional geometry, they see evidence for these directed percolation experiments. How about predator-prey dynamics? Is there any evidence for that? Well, the answer is yes. So very quickly, these are experiments done on two-dimensional magnetized electroconvection, showing as a function of time the turbulent regions merging to form a coherent zonal flow around the outside with predator-prey oscillations. And lastly, in the LH mode transition in fusion plasmas and tokamaks, this a zonal flow going around the outside, the drift wave turbulence going along the axis of the tokamak, those also have predator-prey oscillations that were observed about 5 or 6 years ago. So what I've shown you is, in a nutshell, near the critical Reynolds number, non-analyticities associated with a laminar turbulence transition, if Navier-Stokes arise, just like in all phase transitions. Direct numerical simulations show they are controlled by two modes, anisotropic turbulent fluctuations at small scales, which generates an emergent zonal flow perpendicular to the pressure drop. The zonal flow shears and suppresses the turbulent fluctuations and leads to predator-prey fluctuations as an effective Landau theory for the Landau turbulent transition, for the laminar turbulent transition. In other words, we're treating it as a non-equilibrium phase transition. And then this predator-prey theory not only replicates the behavior that we see in the experiments, but simplifies itself very close to the transition and leaves you with the universality class of directed percolation. So this is remarkable. Navier-Stokes behaves like a lattice non-equilibrium statistical mechanics system. How can a continuum fluid behave like a lattice system? Well, the answer is this. Directed percolation is a second-order phase transition. And second-order phase transitions have a diverging length scale, a so-called correlation length, which in some sense tells you the characteristic size of patches. And that length scale, for generic reasons, near second-order phase transitions, grows arbitrarily large as you get close to the transition, and they become much larger than the lattice. And so directed percolation, even though it's defined on the lattice, actually has a continuum description. And both the Navier-Stokes equations and directed percolation have the same continuum description. So what I've shown you is a Landau theory. It's valid for a single puff near the transition, and it explains the super-exponential time scale dependence on Reynolds number, spatial temporal intermittency, and predicts the directed percolation critical exponents and scaling functions without adjustable parameters, and those have indeed been measured. So the take-home message is that the Navier-Stokes equations quantitatively obey non-equilibrium statistical mechanics at the onset of turbulence. Now, I also think it's true that they also obey non-equilibrium statistical mechanics for fully developed turbulence. That's a story, a very different story, but if you're interested, you can read a summary of why we think that in this paper over here. So here are the people who did the work. This is me and Hongyan Shi, and this is Songlin Si, and we are standing in front of Reynolds's original experiment, which you can still see in the engineering department at the University of Manchester. So let me end with just a very surprising observation. So usually it happens these days that biophysics is a very popular topic. People know that using physics we can create better microscopes, better computer simulations, and so on than has been possible in biology, and this has revolutionized our understanding of biology. It's very commonplace to learn that physics tools help biology. But it's not very often that we see something the other way around. In this project, we had something remarkable. In fact, Hongyan Shi is, when she did this work, she was a student working simultaneously on turbulence and also theoretical models of ecology. Because we understood how to do the biology problem, that enabled us to make this progress on the turbulence problem. So this was an example where the biology actually helped the physics. So this is a fortune cookie that I literally got. It says the turbulence is a life force. It is opportunity. Let's love turbulence and use it for change. And with that, I leave you with the references for the work that I've talked about. So thank you very much for your attention. All right. So that is the end of the formal talks. Do you want to take one of the questions that was asked?
I will very short. Very short.
Okay, yeah. So I'm going to turn the microphone over.
Yes, thank you. It's very nice that somebody also first of all, found the talk interesting and managed technically to put a question in this new format of communication. The question now is not appearing on the YouTube channel, but I remember it quite clearly, and it was about it was found that it's interesting that it's possible to determine pressure using the momentum equation and from velocity information. And then the question was more open, and it was asked, okay, what can we do using the energy equation? And the answer might disappoint partly because the energy equation has a less complex structure than the momentum equation, in that velocity and energy are connected from a scalar relation, especially if we are speaking of an adiabatic process. I would need a pad to write the equation, but we say that in a process where the total enthalpy does not change, velocity and internal enthalpy play I will not say predator-prey to recall your previous talk, but they in fact have to balance each other. So in principle, it's possible to determine the static temperature in the flow. Whether this static temperature is then relevant for some specific fluid processes, perhaps combustion or condensation, this could be a topic for further elaboration.
All right. So let me thank you, the listeners, for staying with us. We have still 90 viewers who have watched this web broadcast during this storm. Thank you very much for your attention. We'd like to thank the Japan Society. There's a question for me. No, I don't. The question for me is, Nigel, can you connect turbulence with directed percolation directly? And the answer is yes. There's two ways to think about directed percolation. One is that it is just the position of a puff, and you think of the puff as being a point particle. And then when you look at the interactions between puffs, you get a model of directed percolation, and you can write down the stochastic hydrodynamics of that. The other, which I talked about, was, again, deriving directed percolation from Navier-Stokes. In other words, the logic was we went from Navier-Stokes to the predator-prey equations. That was the Landau theory for the effective behavior of Navier-Stokes, and that Landau theory, through rigorous renormalization group analysis, then produces directed percolation. So I think that while it is true that directed percolation is the asymptotic universality class for the transition, I think the more important physical point is that once you go slightly away from the critical point, you're still in the regime of Landau theory, but now you have these predator-prey interactions. And you see those modes experimentally. These zonal flows, these emergent modes, you see them in channel flow, you see them in pipe flow, you see them in magnetohydrodynamics. So the fact that the critical exponents are directed percolation is nice, but the more broader phenomenology really comes from the predator-prey dynamics. So one shouldn't think of it as being a bad thing that one derives directed percolation through the predator-prey dynamics, because that is exactly what happens. There's a crossover between two fixed point dynamics, which goes on, and it's very subtle and has very technically difficult finite size effects. And Hisao, I will talk about that tomorrow at Kyoto. All right, so I'm going to wind up. I want to thank the Japan Society for Fluid Mechanics for inviting all of us, not just those of us who were on this broadcast, but all the 6 speakers. We've enjoyed your hospitality, and we wish we could have met you in person. We met some of you. Thank you very much. and the weather has calmed down. So I guess talking about turbulence makes it go away. So with that, I'm going to leave you. I will just say one more thing, that this broadcast is, once I stop it, it will then be available on YouTube, and the same URL will connect to. You'll be able to watch the video of this broadcast again and again if you so desire. Maybe if you have children and they have difficulty sleeping at night, this might be a good way to help them. Anyway, joking apart, thank you very much. We've enjoyed presenting our work. We found it very stimulating, and we hope you did as well. So thank you very much, and good evening to you.